Hello and welcome back to Bioclass Bytes. In this video, we are going to talk about plate tectonics. Don't forget to subscribe to my channel and like and share this video. These are the unit and lesson titles for this video series. In this video, we are going to focus on plate tectonics. In our previous video, we talked about exogenic processes. So those are mountain destroying processes, mostly brought by the sun's energy. But in this video and all the videos in the future, we will be focusing on endogenic processes. These are mountain building processes, building geomorphic processes, okay? So endogenic processes are divided into two. Those that fall under slow movements, or we call that diastrophism, slow movements or slow building movements of the earth, and we also have sudden movements of earth building. Under sudden movements, it's divided into volcanism and earthquakes. Now, I know it might be confusing. Why are volcanism and earthquake considered mountain building or land building? We will learn when we reach this lesson. So, under diastrophism is divided into two: vertical or continental building. We call that epirogenic processes, and they're divided into upward and downward movements. Of the earth. Now, under horizontal or mountain building, we call it orogenic processes. Okay, we will discuss this further. And it's divided into two. Those mountains that are built by forces of compression, that's one lesson. And then those mountains that are built based on the forces of tension. Okay? Endogenic processes are driven by the internal heat of the earth. Okay, that's one major difference between exogenic processes. So exogenic, they derive their energy from the sun. Sun is responsible for most of the water cycle. The sun is responsible for heating up air, causing movement. Sun is responsible for weathering, erosion, and deposition. We've tackled this in the previous video. But in endogenic processes, the source of energy would be the internal heat of the earth. That's why it's called endo, within, from within. Exo, outside, external. So endogenic processes are driven by the internal heat of the earth. Um, and they are called mountain building processes because they create lands, they create mountains, they create continents. Okay, so the heat of the earth bubbles upward, providing a huge driving force, and eventually that bends, cracks, lifts, and moves the earth's the rigid outer layer. Okay, so here, a mountain, Mount Paricutin, is a type of a cinder cone volcano. It is a product of endogenic source of energy. So endogenic forces are those internal forces which derive their strength from the Earth's interior, again, playing a crucial role in the shaping of the Earth's crust. So if you still remember our lesson on the internal structure of the Earth, so we have core at the center, we have mantle, and then we have the crust. So the heat coming from the internal sources are shaping the outside crust of the Earth. So again, endogenic forces are land building forces. They create buildings, they build mountains, they create continents, and earthquake and volcanism, although it's quite confusing, are actually considered land building forces. So for endogenic, endo within, the energy emanating from within the earth is the main driving force again. And this energy is categorized into two: primordial heat of the earth and radiogenic heat of the earth. So the first source of endogenic energy is primordial heat of the earth. Okay, so primordial, it means ancient, old, primitive, first. Okay, so the first ancient heat, this is the heat lost by the earth as it continues to cool down from its original formation. So I know another mind-blowing concept. The earth is cooling down. If you look into our geologic time scale, if you notice that we started out with a very hot earth, so hot that water cannot actually stay in its liquid form on our surface, but now we have, so that's hundreds and thousands and millions and billions of years in the past. So the earth was very hot back then, but now But now Earth has cooled enough that water can actually exist both in its liquid and solid form. So the Earth is continuously cooling down from its original formation. Um, and so that's in contrast to radiogenic heat. So that's later. So the primordial heat is the heat lost, the heat that the Earth loses as it cools down. So the Earth's core heat flow, so that's the heat leaving from the core out into the mantle. So from the core out into the mantle is thought due to primordial heat. So that's around 5 to 10 terawatts of energy. Okay, so terawatts. So that's quite a huge number. So estimates of mantle primordial heat loss is range between 7 to 15 terawatts. So this is the amount of energy that the Earth loses because of primordial heat. So this is a cross-section of the Earth showing its main division and shows us the internal heat flow to the surface. So again, these are the layers of the Earth: the inner core, outer core, lower mantle, upper mantle, and then very thin crust. So as you can see here, the primordial heat originates from the inner core through conduction. So I hope you remember your lesson in physics about conduction, convection, and advection. So conduction, the transfer of energy is when the surfaces are touching. So mostly done by solids, right? Um, so from the inner core, heat is lost into the outer core. So here, this is through the process of convection. Okay? So there's no touching of the surfaces of the material. So here from the outer core, energy is also lost as it moves upward to the lower mantle, and then upper mantle also, and then eventually that heat is released into the Earth's surface. So what's the percentage of the heat flow? So 22% of energy or heat is lost from the core, then around 32% from lower mantle, then 22% are lost or are flowing in the upper mantle, and then 24% on the Earth's crust. So this is the direction. This is the direction of heat flow in primordial heat. So upward towards the crust. So here, if you're wondering, what happens on this site where the heat is released? So this is where your volcanoes are formed. So here, this is the oceanic crust. So these are your underwater volcanoes. These are your hydrothermal vents. These are your mid-oceanic ridges. So that is where that heat comes out. So on land, this is the continental crust on land. So this could be your volcanoes. So that is where materials from the mantle erupts. So that's also a form of heat release or release of energy in that manner. So again, no review of your physics lesson. So conduction, the transfer of energy for those objects that are in physical contact. Example, in your inner core moving out to outer core. So convection, there is no contact between the objects, but the transfer of energy is mostly due to fluid motion, mostly exemplified by liquid and gases. So for your outer core and lower and upper mantle, that's how energy is transferred through convection. And then advection is the transport mechanism of fluid from one location to another. So this is shown by the crust. What's happening on the crust? So volcanic eruptions here, mid-ocean ridges here, movement of the plates here, and all. Okay? So I mentioned a while ago that the Earth is actually undergoing a cooling process. I know that's confusing. How can it be cooling? It's hot and all that. Do not forget that we people are living on the crust. And the temperature here is mostly influenced by the atmosphere, by carbon dioxide emissions. So what I was referring to a while ago, that the Earth is cooling, we are talking about the Earth's geosphere, okay? The internal structure of the Earth. So because of tectonic evolution over time, we've seen the cooling of the Earth as time goes by. So 4.5 billion years ago, okay, 4.5 billion years ago, the Earth is mostly made up of molten magma, molten lava, molten materials. Very, very hot, as you can see here in the temperature scale here. So the Earth is very hot, Hadean period, Hadean Eon. The Earth is quite hot. Nothing, water is not enough water just evaporates. So no living thing here. So that's quite a primitive Earth. Okay, so the Earth is just around 4.5 billion years, by the way. So this is how the Earth looks like when it was initially formed. However, as time goes by, so sometime around maybe here, 2 billion years ago, the Earth has started to cool. So here you have the reduction of your magma, then you have the creation of your primitive mantle, and then the primitive crust. So the Earth is starting to cool down. So no longer molten, some of the materials have solidified and cooled down. And now at the present, so as you can see here, from very hot, now the earth is quite cold, colder. So you still have your magma, you still have your mantle, then you have your modern continental crust and modern oceanic crust. And this is where we are right now. So over time, the earth has undergone a lot of cooling processes. Okay, so from 4.5 billion years ago to modern day Earth, the Earth has cooled down, and this release of energy is mostly due to primordial heat. This map shows us the rate of heat flow, okay, out of the Earth. And do not forget this concept that the Earth is cooling, gradually cooling over time. So Earth loses most of its heat along mid-ocean ridges. So those are plate boundaries underneath our bodies of water. So magma rises, so you can see here color red, very, very high heat flow temperature. Um, Magma rises to fill the cracks formed when tectonic plates pull apart from each other. So that's under bodies of water. In terms of continents or landforms, continents emit more heat than old oceanic seafloor because continents contain higher amounts of heat producing radioactive isotopes. So, radiogenic heat is derived from the radioactive decay of elements found on the Earth's mantle and crust. Okay, so unlike primordial heat, wherein it originates from the Earth's core, so radiogenic heat originates from the mantle. Okay, so four radioactive isotopes are responsible for radiogenic heat. That's uranium 238, uranium 235, thorium 232, and potassium um, 40. So we know that young Earth was very, very hot, okay? Very, very hot because of the heat generated by countless collisions with planetesimals and because of heat release by the decay of short-lived radioactive isotopes. So that's billions of years since origin. So just that during the time when our Earth was formed. But after billions and billions and billions of years, as time goes by, you can see that our energy, the Earth's energy or the Earth's heat, is losing over time. The Earth is gradually cooling over time. So we now have a colder temperature in relative to our origin. Okay. So, so the mantle and the crust contain long-lived radioactive isotopes that we've mentioned. It keeps our planet cooking on similar to a slow burner. Okay, so the energy output of long-lived radioactive isotopes uh, through time is shown here. So the isotopes that we've mentioned: uranium 235, 238, thorium 232, and potassium 30. There's this slight gradual decrease of energy output from these isotopes. Now, we've seen this already. So these are the dominant types of heat transfer at different depths of the Earth. So conduction for the inner core, um, because of solid iron. So conduction and convection for the liquid iron outer core, conduction convection for the rocky mantle, and radiation of energy eventually out into space. So heat travels from the Earth's interior upward through the different layers through convection and conduction, but eventually we lose our heat into space, we release them into space through radiation. In the previous video, we've talked about how endogenic processes are considered mountain building processes and how they derive their energy from Earth's internal sources. So in this video, we're going to talk about one of the two types of endogenic movements. So this one, the first one would be slow movements, specifically the orogenic or mountain building processes. Um, as examples. So we will now focus on diastrophism. Right, those are the slow movements of the Earth's crust. So this was actually taken from the words dia, meaning across, and strophe, meaning turn. So to turn across or to move across. So diastrophic forces refers to the forces generated by the movement of the solid material of the Earth's crust. So mostly we will be talking about plates and their movements. So those are found on the Earth's crust. Slow movements can be classified as horizontal movements, so orogenic, so horizontal movements moving to one side and one side horizontally, or vertical movements up or down, so upward or downwards. Um, so for this video, we'll be mostly focusing on orogenic processes. So they involve mountain building through severe folding and affecting long, narrow belts of the Earth's crust. Orogeny is derived from the terms oro, meaning mountain, and genesis, origin. So how mountains are formed or origin of mountains. So orogeny refers to the forces and events leading to structural deformation of the Earth's lithosphere. Okay, that involves the crust and the upper mantle due to the interaction between tectonic plates. So, according to plate tectonics theory, scientists believe that the Earth is actually broken into slabs and plates, okay, huge slabs and plates, which average around 50 miles in thickness. So, these plates move to one another, on top of each other, against each other, they subduct below each other, above a very hot and deep mobile zone, and they can actually move as great as few inches per year. So these shows us the major plates of the world, the tectonic plates of the world, and they were mapped around second half of the 20th century. So you have here your Pacific plate, Nazca plate, the Caribbean plate, North American plate, South American plate, the African plate, the Somalian plate, subplate, um, Eurasian plate, Anatolian plate here, Arabian plate, Indian plate, Australian plate, then the other half of the Pacific plate, and then the Philippines, we have our own Philippine plate, and then China subplate. So, and then Antarctic plate here, Scotia plate here, and those are the major plates of the world. And as you can see, they are actually interacting with each other. Some are moving towards each other, some are moving away from each other, some are crushing each other, creating all those mountain formations. The plate tectonics theory revolutionized our understanding of our planet. Um, Prior to 1960s, scientists thought that the world is fixed, unchanging, that the landforms have always been there, and that the oceans and seas have always been like that. And when this new idea that suggests that the Earth is actually made up of slabs or of plates of land masses that are constantly interacting with each other, submerging against each other, subducting against each other, um, really was a huge deal during that time because it caused this revolution of ideas. It caused this paradigm shift on how we view our planet. So in the field of geology, the plate tectonics theory is really one of their most important theories. Um, and it is also a unifying theory in a way that it was able to explain the evolution of organisms through time, as well as on the climate system of our planet and other physics concepts, okay, about the nature of our planet. So the plate tectonics theory is supported by two major scientific ideas, the continental drift theory and the concept of seafloor spreading. Now, as we go along, we will take a look at the historical development of the plate tectonics theory, as well as the supporting evidence that made it such a huge scientific discovery sometime in 1960s. So we begin our story in the early 1900s when a German scientist named Alfred Wegener noticed that the coastlines of Africa and South America look like they might fit together. Aside from that, he and his constituents were also able to discover other pieces of evidence that support this idea that the land masses of our planet used to be connected in one giant land mass. He called it as the supercontinent called Pangaea. Um, so according to Wegener, Pangaea used to be connected like this but split apart over time. And the different masses moved away from each other, drifted until they reached their current location. Um, so um, so as we go along, we will see the different pieces of evidence. But I want you to know that when Wegener proposed his work in 1915, it was not readily accepted by the scientific community. It was actually rejected by majority of the scientists because number one, um, Wegener cannot explain how the continents moved. Okay, he had some ideas that he suggested that the tidal waves or the effect of moon's gravity was the one moving the plates. Okay, so the tidal waves was his proposal. However, it was not, it was not sufficient enough to explain how the movement of such large land masses. So it was Wegener's Pangaea idea or continental drift theory was largely ignored when he first published it. However, um, it was still a very good contribution because it paved the way for further research about the nature of our planet. So his idea was not revived until the new technology made exploration of this ocean floor possible. So what was the end product of the continental drift theory? So I've mentioned that was the plate tectonics theory. So plate, that refers to the slabs of land masses. Tectonics, taken from the Greek word tectonikos, which means construction. So it refers to the construction of the land masses of our planet. So the modern plate tectonics theory become widely accepted in 1960s. It states that the outer layer of our planet, or the lithosphere, is actually broken into large slabs called plates. And these plates are constantly moving, okay? Some towards each other, some away from each other, some are subducting from one another. And this interaction of the plates actually results into the formation of our mountain ranges in our oceanic floor. It also tells us the history of our planet on how our land masses change over time. So the movement of these plates not only supports our understanding that the continents are not fixed. Do not forget that this is what we used to think, that the planet is fixed, that it is what it is, that it's always there. But it changed our idea that the planet is constantly changing, that the continents are moving over time. And that also explains why geologic events such as earthquakes, volcanic eruptions are possible. And in biology, it also explains why we can find one type of fossil in this area and then in another country, even if they are separated by large bodies of water. So that's how big of a deal the plate tectonics theory is. It actually explains the history and the nature of our planet and the nature of our land masses and predict what could happen in the future. And that's actually one hallmark of a good theory. It can explain what happened in the past, and it can predict what could possibly happen in the future. So Alfred Wegener was one of the noted scientists who first proposed the continental drift theory, even if his idea was not readily accepted during his time. The first line of evidence that Wegener proposed was the continental jigsaw puzzle. He proposed, so this was actually his drawing of Pangaea when he published his book in 1912. He proposed there that South America fit nicely with the curves of the African continent, while the North America fits with this outline of Europe, okay, and the rest of the world. So this was his Pangaea. This was his supercontinent or landmass, and this was a modern reconstruction of Pangaea. We also see here Alfred Wegener waiting out the 1912-1913 Arctic winter. He actually went to Greenland in an expedition, okay, to study the island's ice sheet. Okay, so that was the first evidence of the continental drift theory. Okay, so that the continents could fit one another like a jigsaw puzzle. Okay, the best fit of South America and Africa. Okay, as well as the other parts of the globe. The next evidence would be geological features. Since the continents could fit each other and they used to be part of one another of this large mass, even the geological features are also similar. So the Appalachian Mountains in North America here, if you compare it with the mountain ranges of Africa, of the African continent, it actually looks as if they fit together or they're connected as um, one mountain range millions of years ago, around 200 million years ago, and that the Greenland mountains in this region is actually almost similar or fits with the mountain regions of Europe, okay, as well as the British Isles. So this is another piece of evidence that supported continental drift theory. Then this one, fossil matches. Okay, so they were able to find fossils of species of organisms on different continents, suggesting that they probably lived on this landmass, and the fossils were found because the animals would just travel across the region. Okay, so the first one would be Cygnognathus, a Triassic reptile which can be the fossils which can be found in South America and Africa. The only possible explanation for that, because this one is um, fossils, these are fossils already. It only suggests that they used to live in this region and then they died in those regions, therefore their remains were fossilized. But as time goes by, South America eventually moved away from Africa, but still the fossil remains. Another one that Wegener saw was the fossils of Mesosaurus, okay, which were found in Argentina and in Africa. Okay, but they are not found anywhere else in the world. So um, imagine that yeah, so this is South America and then this is Africa, and then imagine how large the species that species of prehistoric dinosaur had to swim in order just to reach the other side. So that's quite difficult to imagine. The only explanation for that is that these land masses were actually connected in the past. Same thing with Lystrosaurus, which are found in Africa. They found fossils of this in Africa, in India, and in even in Antarctica. Imagine they were able to find fossils of this. And the fossil fern, Glossopteris, were found in all the southern land masses. So they were able to find it in South America, in Africa, Antarctica, and even Australia. And this is a plant species. They just indicate that all these fossils indicate that all these land masses used to be connected 300 to 200 million years ago. Another major piece of evidence for continental drift theory were the glacial and climate matches. So if you actually, they say that if you actually connect, so this is the modern distribution of the continents. But if you actually connect the southern part of the continent, you could see that they will create this one large glacier, okay? One large glacial feature at the bottom of our planet or bottom of the globe. Um, so it just tells us that they used to be connected and they just happen to drift apart from each other, but still retaining remnants of those glacial features. Okay, so 300 to 200 million years ago, the glacial deposits were all similar on the southern tip of South America, Africa, India, all over Antarctica and Australia as well. Now, despite all these compelling pieces of evidence, Wegener's continental drift theory was largely rejected because what he was only able to propose was the um, origin of the land masses that they used to be connected. But he was not able to actually propose a convincing explanation on how they moved away from each other. So for the longest time, his continental drift theory was not accepted until Harry Hess and his colleagues. So Harry Hess was the one who proposed the seafloor spreading. Okay, so it is he defined it as a process that occurs at the mid-ocean ridges. Okay, so this is the bottom of the oceanic floor. And he proposed that new oceanic crust is formed through volcanic activity. So volcanic activity and gradually moves away from the ridge. So there's this movement upwards of magma and then they move sideways like that. Okay? So, seafloor spreading eventually helps explain the continental drift theory, and together they formed the modern plate tectonics theory. So Harry Hess was actually a professor, okay, a university professor, and a U.S. Navy reservist. So he was actually tasked to in his time he was actually tasked to create a detailed map of the oceanic floor. So as he used the submarines and all the technology of the U.S. Navy, he was able to find the following observations. So number one, that the limbs of convecting mantle, imagine mantle, that layer of the earth, can be found on the upper mid-ocean ridges. So you can find mantle materials that should only be limited in the asthenosphere, but he can find it in the oceanic floor, in the ridges, okay? Oceanic ridges. Then the upwelling of mantle accounts for high heat flow. Okay, that's the area. If you still remember our lesson, that this is where this is where Earth loses most of its heat, okay, along the plate boundaries under the sea floor, and then the entire ocean is virtually swept clean, or virtually a brand new slate of oceanic floor, as it is replaced by new ocean floor every 300 to 400 million years, suggesting that this constant replacement of the ocean floor accounts for the thin deposits of sediments in the deep ocean. Okay, so let's look at those. So that's the first one, the first piece of evidence: mantle material found in the mid-oceanic ridges. The second piece of evidence we've mentioned is the heat flow, okay, along oceanic ridges. So if you actually map it out, you will see that along the oceanic ridges is where new magma is formed, new oceanic crust is formed. Okay, and this is also the part where the earth loses most of its heat. Okay, because magma is being pushed upwards, so heat is being released, and then along that mid-oceanic ridge, the materials are being pushed sideways. So when oceanic plates diverge or move away from each other, it causes fractures on the lithosphere, and it causes basaltic magma to rise up. Now, the second part is very important. They also were able to date the age of the rocks along the oceanic ridges. They discovered that older rocks will be found, so older rocks will be found farther from the ridge, while the younger rocks are found nearer to the spreading zone. So this map out the age of the oceanic lithosphere. So you can see the oldest rocks is in the blue to violet spectrum. So those are found farthest away. So if this is the oceanic ridge, they are found farthest away. While the middle age or the relatively younger rocks are found in the blue and green spectrum. So this is where they can find it. But the youngest rocks, the younger rocks are found nearer the oceanic ridges, nearer the spreading zone. So it only suggests, the seafloor spreading only suggests that magma is being pushed upward on the oceanic ridges where the plates are diverging, and then it pushes sideways the older rocks. So the new rocks are found here from the magma, from the partial melting of the magma, and then being pulled upwards or bursting upwards, and then they push the um, the other existing rocks sideways. Okay, so so those are the pieces of evidence that support seafloor spreading. Now, to learn more about plate tectonics theory, there are several recommendations for you. This one, I'll provide the link in the description below. And this one also, please watch this video, plate tectonics theory lesson. So you see here Alfred Wegener. Again, I'll provide the link in the description below. And then this one is from It's Okay to Be Smart, still about plate tectonics. How do we know plate tectonics is real? Very informative video. You see here um, Pangea and its different um, variations or different supercontinents. Again, linked in the description below. And this one is from PBS Eons, the whole saga of the supercontinents. Now, this one is really like this video because they were able to connect it to biological concepts or evolution of living organisms. So please watch this video, again linked in the description below. Now, so again, no, the continental drift theory, mostly proposed by Alfred Wegener, okay, while the seafloor spreading was proposed by Harry Hess and his constituents. So look at the date, okay, look at the years, around 1930s, just say it's around 1930s, and then Harry Hess around 1960s, the proposal of seafloor spreading. Then the unification, okay, the unification of these two theories into the plate tectonics theory happened sometime in 1963 to 1968. So it took some time. But eventually, the scientists were able to be convinced that the Earth is actually made up of slabs of plates that are moving, constantly moving along the lithosphere. So now we have this modern definition of the plate tectonics theory. It says that the lithosphere, the rocky portion of the Earth is not a continuous shell. It's not one solid shell, but broken into a mosaic of rigid plates that move over the Earth's surface. Okay? And each plate travels as a distinct unit riding on the asthenosphere, which is also in motion. So it says there that the earth is made up of slabs of plates and they are moving along the asthenosphere, and the asthenosphere is also moving. So we have a very active and dynamic earth, always changing, always evolving. I also recommend that you visit this page from National Geographic about plate tectonics. They have a lot of interactive resources there for you. I'll provide the link in the description below. Now, this shows us again Earth's major plates. We've seen this minutes ago. But again, you have your Eurasian plate, Pacific plate, North American plate, South American, African, and Australian Indian plate. Okay, and The lines here shows us the boundaries of the plates. Okay, um, and then here it shows us the type of interaction, okay, of the plates. So for red lines, those are divergent boundaries. It means that the plates are moving, diverging, moving away from each other. While the color blue ones are convergent boundaries, it means that the plates are moving towards each other or against each other. Okay. While transform fault boundaries, these are plates that are rubbing against each other. Okay, so they are not moving away, not moving towards, but rubbing against each other. So if you're interested to see uh, real video pictures or videos in real time of those different plates, I recommend you check out Google Earth. So I will provide the link in the description below. I also recommend that you visit this website, the Geological Society. They have a section there that talks a lot about plate tectonics. So we have three major types of plate interactions. Okay, and the boundary between two tectonic plates is the border between two tectonic plates is called the boundary. So we have three major types of boundaries: convergent boundaries, converge towards each other. So these are examples of plates that are pushing towards each other. Another is a divergent boundary, diverge to move away. These are examples of plate interactions wherein the plates are moving away from each other. And transform boundary, this is when plates slide past each other. So let's look first out at convergent boundary. Again, these are plate interactions wherein they are pushing against each other. They are colliding against each other. So examples of those will be the Eurasian plate and the Indian plate forming the Himalayas. Okay, let's go back to that. So Eurasian plate going against the Indian plate, and this is where your Himalayan mountain range is found. Okay, so this is moving downwards, this is moving upwards. So here you have your Himalayan mountain range. Then the boundary between the Nazca plate and the South American plate along the west coast of South America, you can check that out. Okay, so saan ba yan? Nazca plate, okay, South American plate. So here, this is where your Andes mountain range is found, okay, because they're moving towards each other, then they form a mountain range. Okay, so convergent boundaries can be further classified into the type of plates that are colliding. So you have an ocean to ocean convergent boundary. It means that an oceanic plate is colliding with another oceanic plate, oceanic crust. Okay, so see, they're colliding each other, and then one of them will eventually become subducted. Then it will be pushed downward into the mantle. So an ocean plate collides with another ocean plate, and then one dives beneath the other. This usually forms your underwater volcanoes. Examples of that would be the island arc of the Marianas. Okay, so this is in the Pacific. So this collision eventually caused the release of heat, primordial heat, our lesson then back then, to be released, causing the formation of volcanoes and eruption of volcanoes. Another convergent boundary is ocean continent convergent boundary. Here, an oceanic crust is colliding with a continental crust. Okay, so oceanic crust against a continental crust. So the ocean plate usually, since they are the thinner, so compare the thickness, no? Oceanic crusts are usually thinner than continental crust and they're younger, then they will be the one to dive below the continental plate. Here, mountain ranges or volcanic mountains are formed. So here, underwater volcano. Here, land volcanoes are formed. So examples of that would be the Sumatra and then the Japanese archipelago. Then the last convergent boundary is continent-continent plate boundary. Okay, continent-continent convergent boundary. Here, a continental crust will collide with another continental crust. So two thick continental plates collide, and then they usually form mountain ranges. So this is what happened to Eurasia and Indian. The Eurasian and the Indian plates, they form the Himalayas. So that's what happened. So again, a review: if ocean convergent boundary, they usually form underwater volcanoes, which eventually, of course, as the magma rises, will become islands. Ocean continent convergent boundary will still form, but will still form volcanoes, but this time land volcanoes. Then continent convergent boundaries will create mountain ranges. Okay. So the Philippine region is actually one example of ocean, continent, okay, this one, ocean, continent, convergent boundary. So the Philippine plate is actually subducting or diving under the Eurasian continental crust. Okay, so we know that this will lead to the formation of underwater volcanoes and sometimes even land volcanoes. That's the reason why we have such many volcanoes. Okay, we have one of the most numerous volcanoes in the world. Um, so it creates the oceanic plate. The Philippine plate is actually subducting towards the Eurasian plate, creating which probably created the Philippine archipelago. This is also the reason why we have such deep oceanic trenches. Okay, the Philippine Trench, it's found here, and then Manila Trench somewhere here. It's because this plate is being pushed downward against this continental crust. The Andes is also an example of ocean continent um, collision. Okay, so we've talked about that now. So here, the South American plate is being subducted under the Pacific plate, the Nazca plate. Okay. Let's go back there. Let's check. Yon. So the Nazca plate is being subducted under the South American plate. So this the creation of your Andes mountain continental mountain range. They are it's the longest continental mountain range found along the coast of South America. So because it's being pushed downwards, it caused the formation of this mountain range. So this is another mountain range, the Alps. This is found in Europe. So here the African plate is pushing against the Eurasian plate. So we all know what that happens when continental crust pushes another continental crust. It creates a mountain range. So that's your Alps. Okay, they are the highest and most extensive mountain range system in Europe. Okay, so yeah. So the next type of continental of plate boundary is divergent boundary. So here the plates are moving away from each other. So examples of that will be the Red Sea Rift created by the movement of African and Arabian plate away from each other. And then the Mid-Atlantic Ridge, we'll see that in the example. So here is the Red Sea Rift. You can actually check it on Google Earth. So the Red Sea Rift was created, it's a deep, deep trench, okay? This was actually created by the divergence of the Arabian plate moving this way and then the African plate moving that way. Okay, so they're moving from each other, creating a deep rift at the bottom. So this is the Mid-Atlantic Ridge. This was actually found under the Atlantic Ocean. So here, this deep trench or deep ridge was actually created by along the Atlantic floor by the movement of the um, Eurasian plate and then the North American plate on the northern part, and the in the south, the South American plate and the African plate. So if we go back to that map, so this is where the Mid-Atlantic Ridge, okay, so from this part to this part to this region of the world, that's the Mid-Atlantic Ridge. So the northern part of the Mid-Atlantic Ridge was created by the divergence of the Eurasian plate going this way and the North American plate moving this way. While the southern Mid-Atlantic ridge was created by the movement of the African plate going this way and the South American plate going this way. Because you remember that's consistent with the formation of the Andes, that the South American plate is moving this way because it's colliding with the Nazca plate, which created the Andes mountain range here. It's also consistent with the formation of the Alps, that the Eurasian plate is moving away and then downwards, and it is crushing against the African plate, which created the Alps here. And also with the Himalayas, that the Eurasian plate is moving in this direction. Okay, that's why it's crushing against the Indian plate, which is moving upward. So you have here your Himalayas mountain range. The last plate interaction, plate boundary, is a transform boundary wherein the plates are moving against each other. They are sliding, rubbing up against each other. Okay, examples of that would be the Pacific plate and the Australian plate, and then the boundary between the Pacific plate and the North American plate. So for this Pacific plate and North American plate, this one is the reason why we have the San Andreas fault. So as you can see here, there's the crunching, there's the folding of the fault, okay? Because one plate is moving in one direction, another plate is moving in this direction. So transform plate boundary is the result for that. So this makes the San Andreas quite a dangerous fault because of the stress bit against the rubbing of the Pacific and North American plate, and it's actually capable of generating an earthquake with a magnitude of 7.0 at the moment. So we do not know when that earthquake could happen, but it's quite dangerous plate interaction. This shows us the aerial view of the San Andreas fault. So this is one direction going this way, then the other plate moving this way, as stated here. And then this is the dry channel of the Wallace Creek near Taft, California. This shows us that the seafloor being generated along the Juan de Fuca Ridge moves southeastward past the Pacific plate. So here, this is a divergent plate boundary, and due to seafloor spreading, okay, new rocks or new oceanic crust is being created on this region. While this whole plate is moving downwards, okay, moving downwards, and it subducts, it goes under this North American plate. Now, this interaction of the plates is the one that creates the transform plate boundary along the San Andreas fault. So this will actually be thoroughly discussed when we go to the lesson on earthquakes, but just to remind you, so we measure the magnitude of the earthquake based on the energy it has released. Okay, so we experience a lot of very very mild earthquakes in terms of magnitude. We experience it all the time, but the ones that we actually remember are the ones who devastated the most because of the amount of energy they have released. So those earthquake in 1989, in 1906, in 1800s, they actually have an equivalent of atomic bomb explosion or volcanic eruption. Okay, so in terms of magnitude, some earthquakes are, for those that are between 3 and 4, these are minor earthquakes felt by humans, while 5 to 6 can actually cause property damage. Major earthquake between 7 and 8 can actually have large loss of life and economic impact, and then some could actually have total and mass destruction. So let's review the different plate boundaries. So we have a convergent plate boundary wherein they're moving towards each other, either oceanic, continental, or continental crust collision, right? Convergent boundary. Then we have divergent plate boundary. They're moving away from each other, Right? This is actually exemplified by the seafloor spreading along oceanic ridges. We've talked about that. And then transform boundary, they are moving against each other, rubbing against each other. Okay? Um, so we also have what we call a triple junction, wherein not just two plates are interacting, but three plates are interacting at the same time. So they are the ones seen here in yellow dots. So this region, Nazca plate versus South American plate, here it has several triple junction sites. Here in the Philippine Sea, imagine we have quite a number of triple junction. It means that more than three plates are interacting found along the Philippine region. So that's quite many. Then here is somewhere in Indonesia, Malaysia, New Zealand. You also have a lot of triple junction. Three plates are interacting at the same time. So I recommend that you visit this website from ThoughtCo, defining the triple junction. I will provide the link in the description below. So this shows us the major orogenic belts. So again, a reminder: Oro, mountain; Genesis, Gen, creation. So here it shows us the major orogenic belts of the world created from those plate interactions. So here you have the Andes. Here you have the Himalayan mountain range. Here you have the Alps. Here. So all of those were caused by the crumpling and pushing of plates towards each other, which formed these mountain ranges. So we call this creation of mountain ranges as orogenic processes or orogeny. So it's the primary mechanism by which mountains are built on continents. So the movement of tectonic plates is thought to be the product of convection currents in the mountain. And we've established that deep within the Earth's core, heat is generated by the radioactive decay. Okay, those are the loss in the primordial heat of the Earth. So, and then what happens is as this energy is released, they are released from the core into the mantle, out into the crust, and that is the reason for the movement of the plates in those examples that we've talked about. So they could either collide, slide by, or diverge from each other. So these are the products: the Himalayan mountain range, the trenches found on the floor, volcanoes, and islands. That ends our video. I hope you learned something new. Don't forget to subscribe to my channel and like and share this video. Till next time, goodbye.